Morning everyone. My name is Atharva Gurukute and I am a student of third year BTech in Computer Engineering at MIT Academy of Engineering, Alandi. Today I am going to present a very important and interesting topic, optimization of loss function and getting best fit line using gradient descent. This topic lies at the core of machine learning and data analytics because almost every predictive model uses the concept of minimizing error, or in other words optimizing the loss function. So through this presentation I will be explaining three main things: the concept of regression and the regression equation, the role of loss function, and how gradient descent helps in optimizing the model and finding the best line. So let's get started. Introduction. Let's start with the basic idea. What is regression? Regression is a statistical technique used to study the relationship between two variables. In simple words, we try to understand how one variable affects another. For example, let's say we are studying how many hours a student studies and how many marks they score in an exam. Here, the independent variable is study hours and the dependent variable is marks. By plotting this data on a graph, we get several data points, and regression helps us draw a line that best represents the relationship between those points. That line is called the best fit line. This line allows us to make predictions. For instance, if a student studies for 5 hours, we can use the regression equation to predict how many marks they might score. So, regression helps us understand trends, make predictions, and find patterns in data. Regression equation. The most basic form of regression equation is simple linear regression, where we deal with one dependent and one independent variable. The equation of straight line is given by y equal to mx plus c. Here, y is the independent variable, the one we want to predict. X is the independent variable, the input variable. M is the slope of the line, it tells us how steep the line is, and c is the intercept, the point where the line cuts the y-axis. So our goal in regression is to find the right values of m and c so that the line fits the data points as closely as possible. Now you might be wondering, how do we know whether our line is a good fit or not? That's where the loss function comes into play. What is optimization? Before jumping into loss functions, let's understand what optimization means. Optimization is the process of adjusting model parameters, in this case M and C, to make the model perform better. In simple words, we want to find the best possible values of M and C that minimize the difference between the predicted and actual values. Think of it like tuning a musical instrument. You keep adjusting the strings until you get the perfect sound. Similarly, in optimization, we keep adjusting the parameters until the model gives the most accurate predictions. The mathematical tool we use to measure how wrong our predictions are is called the loss function. Loss function. Now let's talk about the loss function, also known as the cost function. The loss function measures the error, that is, how far our predicted values are from the actual values. The most commonly used loss function in regression is the mean squared error, or MSE. The formula for MSE is MSE equal to 1 upon n summation of y prediction minus y actual the whole square. This means we take the difference between predicted and actual values, square it, and find the average across all the points. Why do we square the difference? Because if we didn't, positive and negative errors would cancel each other out. Squaring also gives more weight to large errors, which helps improve accuracy. Let's take a simple example. Suppose a student's actual mark is 80, but our model predicts 70. The error is 80 minus 70 equal to the whole square equal to 10. If another prediction is 95 when the actual is 100. The error is 100 minus 95 equal to 5. The squared errors are 125. By averaging this, we get the MSC. So, the smaller the MSC, the better our regression line fits the data. Why minimize loss? Now, why do we need to minimize the loss? Because minimizing the loss means making our predictions as accurate as possible. A smaller loss indicates that our predicted values are very close to the actual values. Think of it like target shooting. If our arrows are close to the center, your error is small, which means you are accurate. If your arrows are far from the center, your error is large, which means your model needs improvement. So, the goal of optimization is just like aiming for the center to reduce the error, or in our case, to minimize the loss function. Gradient descent introduction. Gradient descent is one of the most popular and widely used algorithms for optimization. It helps us find the values of m and c that minimize the loss function. It works in an iterative manner, meaning we start with some initial random values of m and c and then gradually adjust them step by step to reduce the loss. After every iteration, the algorithm looks at the direction in which the loss function decreases and it moves in that direction until it finds a minimum point, the point where the loss is smallest. This process of gradually moving toward the minimum is called gradient descent. Concept of gradient descent. Let's understand the intuition behind it. Imagine you are standing on the top of a hill and your goal is to reach the bottom of the valley, the lowest point. You can't see the entire valley, but you can feel the slope beneath your feet. So you take small steps downward in the direction where the slope is steepest. You can you continue taking such steps until you reach the bottom. In the same way, gradient descent helps us reach the minimum point of the loss function where the loss is the least. At each step, the algorithm calculates the gradient, which is the slope of the loss function, and it updates the parameters m and c in the opposite direction of this gradient. That's why it's called gradient descent. We are descending along the gradient to minimize the loss. Mathematical steps. Now let's understand the mathematical steps involved in gradient descent. Initialize the parameters m and c with random values. Predict the output using the equation y equal to mx plus c. Calculate the loss using the MSC formula. Update the parameters using the following equations: m equal to m minus alpha into del m upon del m, c equal to c minus alpha into del l upon del c. Here alpha is the learning rate which controls the step size. Repeat these steps until the loss stops changing or becomes very small. This iterative process ensures that we gradually move toward the minimum loss value and find the best M and C. Learning rate alpha. The learning rate is one of the most important hyperparameters in gradient descent. It decides how big a step we take in each iteration. If the learning rate is too large, we might skip over the minimum and fail to converge. If it is too small, the algorithm will take tiny steps and become very slow. For example, imagine walking down a hill. If you take very big jumps, you might overshoot and fall. But if you take very tiny steps, you will reach the bottom, but it will take a lot of time. So, choosing the right learning rate ensures a balance between speed and accuracy. Visualization of gradient descent. If we visualize the loss function on a graph, it often looks like a bowl shape. The top of the bowl represents high loss and the bottom represents minimum loss. At the beginning, when the model parameters are random, we start somewhere near the top of the bowl. As we apply gradient descent, we keep moving down the slope and the loss value decreases. Finally, we reach the bottom of the bowl, the lowest point where the loss function is minimized. That's when our model is perfectly optimized. Convergence. Convergence is the stage where gradient descent stops updating parameters because the loss value becomes stable. In other words, further updates don't make much improvement. At convergence, the algorithm has successfully learned the best value for M and C. This is the point where we say our model has learned the optimal parameters. After optimization, we finally obtain the best fit line, the line that minimizes the total error between predicted and actual values. This line passes as close as possible to all the data points, giving the most accurate predictions. The best fit line can be used for future prediction tasks. For example, predicting the marks of a student based on study hours or predicting house prices based on area. Example, let's take a simple numerical example. Suppose we have the following data. R studied is 2, 4, 6 and 8. Marks scored are 40, 50, 60 and 80. Initially, we assume some random values for M and C, say M equal to 0.5 and C equal to 10. Using these values, we calculate the predicted marks for student. We then compute the MSE to see how large the error is. Using gradient descent, we adjust MNC step by step to reduce this error. After several iterations, we might get M equal to 5 and C equal to 20, which perfectly fits the data. So our regression equation becomes y equal to 5x plus 20. Now if a student studies for 7 hours, we can predict their marks as y equal to 5 into 7 plus 20 equal to 55. This is how gradient descent helps us make accurate predictions. Applications. Descent is not limited to linear regression. It is used in almost every area of modern data science and machine learning. Some major applications include machine learning to train algorithms by minimizing error, deep learning used to update weights in neural networks, finance and economics for predicting stock prices, inflation or economic trends, data analytics to find relationships and optimize data models, artificial intelligence to make models smarter and more efficient. So, whether you are training a simple regression model or a deep neural network with millions of parameters, gradient descent is at the heart of it all. Conclusion. To conclude, gradient descent is one of the most powerful optimization techniques in machine learning. It enables models to learn by minimizing the loss function and improving their accuracy step by step. The combination of regression loss function and gradient forms the backbone of predictive analytics. It's the starting point of understanding how complex models like neural networks actually work. Once we understand this concept, we can apply it to advanced algorithms like logistic regression, support vector machines, and deep learning models. Thank you.